So what we're going to study in this section is something called the effective nuclear charge, and it's the setup for the next section in which we look at all the periodic properties, or many of the periodic properties of the elements, and their relationship sort of to quantum mechanics and what we know about the structure of the atom now. So what is effective nuclear charge? So very simply put, is if you're an electron in the atom, and let's just say you're this electron. This is a lithium atom. And lithium Z is equal to 3, third element on the periodic table. So it has a nuclear charge of plus 3. The outside electron only experiences a plus 1 charge. And the way you calculate the effective nuclear charge, and we usually just call it Z effective, right, is equal to Z, which is my atomic number, minus the screening electrons. The screening electrons are all the electrons in the core that sit below the outermost electrons. And you can actually do this calculation for any atom, or any electron in the atom. But for this valence electron on lithium, it sees an effective nuclear charge of plus 1 because I have a 3 plus nucleus. I have 2 screening electrons. Those are the electrons in the 1s orbital. And so I get a 1 plus as my effective nuclear charge. Now, if you're the 1s electron, and I want Z effective for that, well, it's 3 minus, and because you're in the 1s orbital, the way we're treating this is there's no screening electrons because you're next to the nucleus, and so this would be minus 0. And so you'd have a 3 plus effective nuclear charge. So in fact, what happens to the innermost electrons with this sort of effective nuclear charge, because they don't see any screening, they actually get drawn in much more tightly than the electrons that are on the outside of the atom. So I wanted to show you sort of briefly how the effective nuclear charge varies on the periodic table, assuming that we're still using this approximation that you just take the screening electrons and subtract it from the nuclear charge. So you think about nuclear charge in any position of this periodic table. Hydrogen's up at the top left, so the nuclear charge here is 1, right, 2, 3, 4, and then 5, 6, 7. I'm not going to do the whole thing, but 8, 9, and 10. So that's the effect. That's the nuclear charge. Now, if you're looking at n equals 1, then the effective nuclear charge is just a nuclear charge because those are the 1s electrons. Now, when you get up to this point here, this is the filled electron configuration 1s2. Okay. Now, when you go to the next energy level down, so this is n equals 2, right? Then what you get to do is you get to subtract these electrons off from the nuclear charge. So what that'll do is that'll change the situation so that instead of, for example, for lithium, this is the one we did as an example, instead of the effective nuclear charge being 3, like the nuclear charge was just the effective nuclear charge for the first period, then what happens is the Zeph is 3 minus 2, so this becomes 1. Well, for beryllium, the effective nuclear charge is 4, and then it's the same core, 1s, right? So this becomes 2. So if I go to boron, this will be 3, and then 4, 5, 6, 7, and 8. So the positive charge, that's what this is, the positive color, is Zeph, right? Equals positive charge experienced by the valence electrons. So you'll notice all I really did then is I subtracted the 2 electrons from the 3 electrons and etc. all the way down the line. Now if I do n equals 3, then I have, for example, for sodium, I have 11, and then 12, and 13, 14, 15, 16, 17, and 18. So how do I calculate effective nuclear charge for these, right? So for those guys, I'll use a slightly different color. Zeph would be equal to 11, that's the nuclear charge, minus the core, which now is 10. So what I'm going to get is 1, right? And then for this one, Zeph is 12, but I'm still subtracting 10 because that's the core that's common to the whole group of them, the whole period of them. So then this will be, again, 1, 2, and then guess what, right? 3, 4, 5, 6, 7, and 8. And you notice what has happened sort of in our simplified treatment of effective nuclear charge. The effective nuclear charge experienced by any atom in a group is the same. And so sort of the type of chemistry we can expect for each of these elements as we go down from left to right, the properties of the elements as we go left to right should vary to about the same amount as I go around the periodic table, provided that, for example, I'm looking at going from 7 to 8, I should see similar trends from 15 to 16 because the change in the effective nuclear charge approximately is the same. And these are, in fact, the things that Mendeleev was seeing when he was looking at his periodic table. He was taking properties like densities or masses, in particular, is where he started, and subtracting them and saying, well, gee, what's happening to the masses here and the masses here? But then he also went on to do densities and a number of other different properties. So I want to very quickly talk a little bit about the transition elements. And we won't say much more about it in this chapter. But the first transition elements are experienced on the 4th period here. So I'll do purple. I guess that seems appropriate. Oh yeah, the transition elements makes a lot of the brightly colored compounds that we see on the periodic table. So if I'm going to just put in the atomic numbers here, this is 19, 20, 21, 22, 23. And now what we're going to be talking about specifically is effective nuclear charge experienced by the valence electrons, right? So what's going on is that, for example, for potassium, the effective nuclear charge is going to be 1 because I take 19 and I subtract 18 from it, right? And then I get 1. This is going to be 2. But now think about what's happening here. These are the n-1 electrons. These are still the valence electrons. So I'm going to be adding an electron into the core and adding a proton into the core every time I go across here. So while the charge goes up, right, the shielding goes up, and the effective nuclear charge that these electrons experience is roughly the same all the way through the transition metal series. So what happens is then, when we see trends in the periodic table, the trends for the main group elements, that's these s electron elements and these p electron elements, follow a distinctly different pattern than the transition elements. And some of the stuff that we see very clearly in the main group elements, right, we don't see in the transition elements. We do see trends, but it's a little bit more complicated of the relationship of the trends. One of the complications is the idea that here the screening of electrons, we just say it's a one-to-one correspondence, that I have one electron and it screens one nuclear charge. That's not as true. It's actually less true for the transition elements. And one of the things we don't take into account is how the shape of the orbital and penetration really affect the ability of an atom or an electron to screen other electrons. Because of the number of lobes on the transition element orbitals, the d orbitals and the f orbitals, remember the lobes are that like this shapes, like this, right? They're actually not as effective at screening the nuclear charge, simply because they don't block the space out as well, plus their orbitals stick further out rather than around the nucleus. So anyways, we're going to focus mainly on the main group elements, the A groups, right? And the transition elements, actually, we save that for a later chapter in next semester. But the trends are understandable when we get there, but we're going to be focusing mainly on the A's, the main group elements. So just as a quick summary, right, the effective nuclear charge is the positive charge attracting an electron to the nucleus. Z is nuclear charge in this equation, that Z effective is equal to the nuclear charge minus the screening electrons. And I just made the note that not all the shielding is the same. The trend is, generally speaking, S's are best at screening, P's are next, D's, and then F's are the worst. Okay. So in essence, not the full nuclear charge is experienced by the outermost or valence electrons.